Hi everybody, this is the second day of analysis. And I want to start off by calling the roll, and I think we have significantly fewer people here today. Mariah's not here yet. Jonathan is here. Dalvin's not here yet. Samantha's not here. Corey is here. Brad is not here. Melissa is here. Chuck is here. Mary is here. Adam is not here. Audra's here. Megan is here. Mark is not here. So that's what it might have been the case that last time we had more attendance than what's normally going to be the case. And this might be the kind of core group that we have more often than not. Although I do believe one other student will be joining us on a regular basis who's not here today. At least one other student. Last time we were talking really about preparatory work in terms of proving techniques. And we had done several proving techniques, and I want to continue with looking at a couple more proving techniques today, and then doing a little bit more preparatory work before we get into something that's of the substance of the class in terms of course material. Okay? Good to see you. This next proving technique, I think it's our fifth one. It deals with a certain type of if-then statement. So the fifth proving, so this proving technique is concluded. It says if P, then, this is the type of statement that I'm worried about proving, then Q or R can be proven by assuming P. So it puts us in position of when the statement would apply. And then we have two steps here. If Q occurs, then the statement is true. So just noting that. And number two, the only other option is if assuming Q doesn't occur, we must prove R occurs. So this, to me, is a really nice, logical progression. Someone constructed this way thought of proving this if P and Q or R statement by this means. I really am kind of in admiration of this thinking, so I want to explain it a bit more. To prove if P then Q or R, for that statement to be true, that is when P happens, this statement to be true, then Q had to happen or R had to happen for the statement to be true. Okay? Both of them could have happened. At least one of them has to happen. And so this proving technique says, look, we have to assume that P occurs. And then we say, well, if Q did happen, the statement is true. So if we assume Q happens, we're done. The only other case is if Q didn't happen. And in that case, we have to show that, for the statement to be true, that R had to happen. Why is that such a nice kind of a structure for trying to be able to prove these types of statements? Is that we're assuming that P is true, and essentially we get to also assume that Q is not true. That means we get two things of assumptions, things that we can work with to logically progress, as opposed to only having one thing to work with. And so that's a very nice logical rearrangement of how to prove this statement. Okay, so I'd like to show an example of this. And if the sum of a real number with itself is equal to its square, then the number is 0 or 2. That's the statement. We want to prove it. Right. Back, we just get started. We're not very far. We want to prove this statement. If the sum of a real number with itself is equal to its square, then the number is 0 or 2. In other words, the statement is if a number with itself, the sum of a number with itself, that's if 2x equals to its square, x squared, then x equals to 0 or x equals to 2. That's what we're trying to prove. If x plus x, which is 2x, equals x squared, then x is 0 or x is 2. Okay. I'm ready to do the proof in this manner. So the first thing I'm going to do is we're going to assume p happens. So suppose 2x equals to x squared. This, we want to show that either x is 0 or x is 2. Well, if x is 0, we're done. Because the statement will be true. Then, let's see what. Then the statement is true. If x is different than 0, what do we have to prove? It must be 2. Right. For the statement to be correct, we must show that x is equal to 2. Okay. So here's what I'm going to stress. I'm going to say since x is different than 0. Okay, so x is some real number and it's not 0. What that means is that its multiplicative inverse exists. Okay? There's some guy out there, a real number, that you can multiply this particular x by and get 1. Okay? 1 over x is a real number. Since 2x equals to x squared, that's what we're assuming, then I can multiply both sides by 1 over x. So that means that, if you will, 2 times x times 1 over x will be equal to x squared times 1 over x. And so, when you complete this multiplication, on the left-hand side, you're going to get 2. And over here, on the right-hand side, what are you going to be left with? X. So x had to be 2 if it weren't 0. Thus, the statement is true. And that ends that proof. And I put the box to say that ends our work. Does anybody have a question about what we did there?
So is it just our common courtesy to prove both Q and R?
What we're doing in this type of situation, we're saying if Q occurs, we're done. The statement is true. Okay. But if Q isn't done, there is work to be performed, and that work is to show that the R is done. So it doesn't have to do with courtesy, it has to do with proving the statement.
With an
Right. But that, with the way that we're setting up the proving technique, we get to use an additional assumption in the structure. So that's what I admire about this proving technique. It's somehow we constructed a way to get a little bit more information out of the problem. Is that okay what I said?
Is there any particular name for it?
If there is, I'm unaware of it. So there might be, but I don't know. Sometimes I will call it, this is my made-up expression for it, is the previous proving technique I call proving by cases. But this is really proving by cases, but it's on the conclusion as opposed to the hypothesis, the assumptions. Okay? So I'll say this is proving by cases on the conclusion. The last proving technique I want to talk about is a proving technique for statements about natural numbers. And so, I think this is our sixth proving technique. And this is proof by induction. And this is used to prove statements about or involving natural numbers. To prove a statement is true by induction, I want to say statement is true for each natural number by induction. I'm going to stop, give you a second to catch up. Plus, this class makes me drink. I need a second. I have cut down on my caffeine consumption, and I'm making much more mistakes. That's what's happened. So I'm really ticked off about it, to tell you the truth. The biggest mistake that I think I made was that Dr. Lee is not here currently. And so I said to you that I'm substituting for him. I thought all of his classes were on Tuesday, Thursday. They're not. So I missed his Monday class. And this is a person who has subbed for me in the past in this manner, okay? One time I asked him to sub for me because I was out of town, and he had an emergency. He was in the emergency room till about 4:30 or 5 o'clock in the morning, and then went to teach my class at 9. And so someone who's willing to do that, has that much determination, you should be able to repay him back by, going to the classes that he asked you to. And there was nothing that prevented me except ignorance, not being able to read when his classes were. So I'm really embarrassed about it. Look, I've told that story to kind of give us a chance to catch up. But I want to emphasize here, what we're trying to do by induction is prove a statement that is made for each natural number. Okay? And here's what we want to do. We're looking at a statement that says, this statement is true for each individual natural number. Well, if it's true for each natural number, then it better be true for the first natural number, which is 1. So to do this by induction, we show the statement is true for n equal to 1. And here I'm going to say n equal to 1. It's for 1, okay? Then, that's the first step. And the second step, I'll write up here. The second step is that we assume the statement is true for n equals to k. That's an arbitrary, fixed natural number. We must show the statement is true for n equal to k plus 1. As you write this down, is it okay if I erase the side? Well, I'm going to say something. I think about proof by induction analogously to a fad that was occurring when I was a youngster. So one of the fads that was occurring when I was a youngster is that people would go to the gymnasium on the gym floor, set up thousands of dominoes on edge, such that they were close enough to each other that once you knocked over the first domino, it would hit the next domino after it knocked it down, and knock down that next domino would knock down the one following it. And so they would set up elaborate patterns, and so the domino that would fall would hit the next domino and cause it to fall. And that's what I think of as proof by induction. First of all, you've got to make sure we're trying to say the statement is true for all natural numbers, for each natural number. Meaning we've got to knock down each natural number for the statement. Okay? The first thing you've got to do is be able to knock down the first natural number, the statement for the first natural number. That's n equal to 1. That's the first domino that's got to get knocked over. And then what you've got to show from there is that once a domino is going to be knocked over, whatever it is, it's going to knock down the next domino. Is that okay? And that's the way that I think of it. Once the statement is true for a particular arbitrary k, it's going to make the statement true for the next one. So as an example, someone might say, prove that the sum as I run from 1 to n of I of I is equal to n times n plus 1 over 2. Prove this formula is true for each natural number n. So that's what I want to do. This is a well-known fact. The first time that when I teach that I show this fact or use this is in Cal 2, essentially, into Cal 1. Before I prove that, let us just make sure that we understand the symbolism involved. This notation here, sigma, here, capital sigma, Greek letter, means to add what follows. What follows here is a formula. And the formula changes depending on what I is. Okay, what we get out depends on what I is. And I is going to run from 1 to n, where n is some natural number. And the answer is supposed to be whatever that top natural number is, times 1 more than what it was, all divided by 2. And so just to, before I do proof, let's do an example to see that that is true. Let's say when n is equal to 3. Example. When n equals to 3, here's what the statement is that I running from 1 to 3 of I, it's that sum. The sum is I runs from 1 to 3 of I is equal to 3 times 4 over 2. Let's check it out. The sum is I runs from 1 to 3 of I. What's that equal to? It's equal to 1 plus. So when I is equal to 1, I just got 1. Well, then you let I be the next number, which is 2. So I add, sum means add, so 2. And then I'm going to add whatever occurs next for this formula. Well, that's when I is equal to 3, we get out 3 for this part. And that's where I stop. It's at 3. So when I look at this, this is 6. Also, 3 times 4 over 2 is equal to 12 over 2, which equals to 6. So these quantities are the same. Okay? So what I've just shown is that this formula is true when n is equal to 3. But I don't not only want to show that it's true for when n equals 3, I want to show it's true for n equal to 1, n equal to 2, n equal to 3, n equal to 4, and forever. Okay? For every natural number. And I can't do, that's the work it is to show it for each natural number. 3. And they're going to get, when these get bigger, the string is going to get a lot bigger. So and you can't do it for each individual one directly. So we use proof by induction. So here's my proof by induction. And I would tell the reader, it's by induction to kind of give them a heads up. Hey, look, that's the way we want to do this. So here, when n equals to 1, the left-hand side is the sum, as I know I'm writing very small, as I runs from 1 to 1 of I. The left-hand side of the form. That means in this summation, there's only one term. When I is equal to 1, we get out 1. And what do I add up to? When I is equal to 1. So there's only one term. Now, n over n plus 1 over 2, when n is equal to 1, is equal to 1 times 2 over 2, which equals to 1. So we see the statement is true when n equals to 1. I'm going to write that out very formally. So, this formula is true when n equals to 1. So that's the first part of induction. I've done that. The second part of induction is we're going to assume the statement is true for when n is equal to k. That is, here's what we're assuming. We're assuming the sum as I runs from 1 to k of I is equal to k times k plus 1 all over 2. I'm just replacing in the generic formula where there's an n, I'm putting in k. That's all I'm doing. Okay, so we're assuming that. From that assumption, what is it that we're trying to show? We're trying to show the statement is true when n is equal to k plus 1, Corey said that. Yeah, Corey. I'm going to write that down. So we must show the statement is true for n equal to k plus 1, and more specifically, that is, we must show the sum as I runs from 1 to k plus 1 of I equals, there's I, there's a little mark on the board, I hope it's, okay, that's just an I, is equal to k plus 1 times k plus 1 plus 1, so that's k plus 2 over 2. That's what I got to show. I'm replacing the n in the formula, in this case of what we're trying to show, by k plus 1. Let me have your attention just for 1 second. So this guy's k plus 1, this guy's k plus 1. K plus 1 plus 1 is k plus 2. That's what I'm saying is what we got to show. And we're going to prove that, we're going to get that result based on our assumption that the statement is true for k. All right, I'm ready. Note, this sum, as I runs from 1 to k plus 1 of I, what's it equal to? It's equal to, well, it's equal to 1 plus 2 plus 3 plus, what's next? 4. And you keep going. What's the last term that I have here?
K plus 1.
Okay. And that can be rewritten as 1 plus 2 plus 3 plus 4 plus, let me put in the next to last term. That's k. Plus k plus 1. Is that okay? But wait a minute. The sum of the first k terms is something I know about. So if you want, I can say, hey, I do want to. This is the same thing as the sum as I runs from 1 to k of I. Look, wait a minute, look at it. That sum is up to here. That's all these guys. So it's that quantity. I put it in parentheses. Plus what's left? K plus 1. That's correct. But by assumption, I know, from what I'm assuming, I know what the sum of the first k numbers is. What's that? So what do I write down?
K times K plus 1 all over 2.
Plus k plus 1. Okay. Now remember, I'm trying to get this answer. I'm trying to get this. So this guy better be equal to that, and it is. I just need to do some algebra at this point. Okay, to simplify where we are, what I'm going to do is just get a common denominator. So I got k plus 1, I got k times k plus 1 over 2. Isn't that what it says over there? The common denominator is 2. So I'm going to say plus 2 times k plus 1 over 2. And so I can factor out the k plus 1. So I get k plus 1, and really it's all going to be over 2. When I factor out a k plus 1 here, I'm left with a k. When I factor out a k plus 1 here, what am I left with?
Plus 2.
K plus 2. All over 2. Isn't that what I wanted to show? That's it. That ends the proof. Anybody with any questions about what I did there? If you want to write the conclusionary statement, so by induction this formula is true, write down the formula, it's okay. I'm just going to end it there. That's it. That's what we set out to do. That's good enough. Done. There's one more type of statement I want to address. I think it's the seventh one. I'm not going to do an example of it. They're going to come up in class. But we can prove, I just want to translate what we have to do. We can prove P if and only if Q, if and only if. Look, we mathematicians don't write out the words if and only if. We abbreviate. And so the abbreviation is IFL. Q. By proving two statements. One is if P, then Q, and the second statement, so 2, if Q, then P. So we've got to prove both of those statements. So we're saying if P happens, then it follows that Q will occur. And if and only if statement, if Q happens, then P will have to occur. One indicates the other will happen. So I'm not going to do an example of that. It'll come up in class. We'll break it down in those two directions. Essentially, if and only if statement becomes two if-then statements. So it's like two proof problems involved. Okay. As I erase the board, I just want to mention something. Megan said that she was able to access via my SSU, the Blackboard site, and was able to see the video that we had the first day. Maybe others have tried that too. So the syllabus is online. Okay, I'll hand it to you, as well as the first video. And I'll put this next video up later today, I believe. If you want to watch it. Okay, the next thing I want to talk about is some symbolism that we'll use. I just did an abbreviation just a second ago, so I'm going to write up some abbreviations. So these are some common abbreviations in mathematics. So one is IFF means if and only if. By the way, IFF is an official word in Scrabble. Okay? So for those of you who are interested, you can play that word. I will tell you that the word quicklier is not a word. If you get challenged, you're going to lose. Sounded like a word to me. This symbol here means element of. Okay? So it belongs to a collection. 3. This symbol here means, so this backwards capital E, there exists. This symbol won't be used that much in this class, if at all, but an exclamation point in symbolic notation. We're not talking about factorial. This means unique. That's the symbol for there's a unique answer. 5. This backwards element, so it's not a backwards E in this form. It's not a capital E. It's more like this guy put backwards. Or I will just write down this. Means such that. Lots of mathematical definitions and analysis and statements have the phrase such that in it. And the first time I took a proving class, I thought that it was a pet phrase of my professor. I thought that professor sure likes saying the word such that. I didn't even pay attention to the book to know it's in a lot of the definitions. She was just quoting what's commonly done. I thought it was a personal preference phrase for her. It's not. Something we use in mathematics a lot. 6. That symbol right there, that upside down capital A, means for all. So those are some common symbolisms that I'll use. I think the last thing I want to do before we get into beginning course material, basic course material, is I want to talk about some basic sets. First of all, we have the empty set. That's this guy, or null set. That's symbolized this way. And these are sets that contain nothing, contain no element. All right, the next set I want to talk about is the set of natural numbers. That's denoted by script N. I'll write it this way. and it's equal to 1, 2, 3, whatever. Thirdly, a set of rational numbers. What that is symbolized by Q. And kind of write a definition of Q, rational numbers, up here. Well, I made a mistake. Let me back up. I'm sorry. I'm sorry. The set of integers is represented by Z, which is equal to, well, it's infinite. You have -3, -2, -1, 0, 1, 2, whatever in this direction. That's the set of integers. Now let's do the rational numbers. They're symbolized by Q, script Q. What they're equal to is a set of fractions, A over B, such that big line means such that. That's another symbolism, such that. In set notation, put a big line, or colon sometimes. A and B are elements of the integers with B being different from 0, because you can't divide by 0. And I think that that's enough in terms of sets that we'll look at. But in terms of symbolism, we have to figure it one more. 5, the real numbers, I'm not going to define them here, but the real numbers are symbolized by script R. That's what I'm saying. That's just simple. Some people would define the real numbers as any number that has a decimal representation. Other times, mathematicians set up things talking about Cauchy sequences of rational numbers and all of the limits of all the Cauchy sequences of rational numbers. The limits of them, that forms the real numbers. So they have different ways of defining them. I'm just going to say, hey, we know what the real numbers are. I don't know what they're eating. Having said that, I'm ready to do course material. The first course material is really something out of the book, found on either page 23 or 24, depends on what edition. And it's the algebraic properties of R. And that's what I'm going to look at. Algebraic properties of R. It's got a prefacing statement. It's something like, on the real numbers, there are 2 binary operations plus addition and multiplication. Is that right? Is that what it says? People looking at it? Yeah, I look at it. And that they satisfy about 9 conditions. Okay? This is on page 23. It's on page 24 for the newest version, most recent edition. It says on the set R. Okay. There are 2 binary operations. Denoted by plus and dot and called addition and multiplication. These operations satisfy the following. So there's 9 things. What are the 9 things? So the first one is this. The first one is A plus B is equal to B plus A. And that's for all A, B, and R. That's the commutative property, okay? First thing happens. Then there is the associative property. So A plus B grouped together, then added to C is the same thing as A plus B plus C, where B and C are first added together. And that's true for all A, B, and C, and R. You guys that have the book open, make sure that I'm not missing anything, okay? The third thing is there exists a number 0, so this number 0 in R, such that, I'm going to write it this way. A plus 0 equals to A for all A excuse me, in R. This is called the additive identity. There's this number out there that when you add it to another number, you just get the number, the original number you added. That number is 0. Well, there's something, since we have the existence of 0, for each real number, there exists a real number, we'll call it minus A. For each real number A, there exists a real number minus A that such that A plus minus A equals to 0. That minus A is called the additive inverse. It's the guy that you add to A to get back to 0. Well, those are the 4 main properties for addition. Now, there are 4 similar properties for multiplication. So 5 is that A times B is the same thing as B times A. That's true for all A and B element of R. Sixthly, A times B, multiply together first, then times C is the same thing as A times the quantity, B times C. So that's associativity for multiplication. And that's true for all A, B, and C element of R. Seventh one, there exists a number, real number, 1, different from 0, such that A times 1 equals to A for all A element of R.
Now, is that 1 or such that? On 7.
So here, there's this a number 1, different from 0, such that.
Okay.
A times 1 is equal to A.
The borrowing such that and set notation, right?
Yes, that's what we're thinking of, yes. So that is a 1. Yes, I see what you're asking. That last property is saying that there is a multiplicative identity. It's 1. 0 is the additive identity. Okay, an eighth property is that right this way. For A different from 0. So for all real numbers that aren't 0, there exists a real number one over A, satisfying or such that A times 1 over A is equal to 1. So you give me some non-zero number, there's some number out there that if you multiply that given number by, you get 1. That is saying that there exists a multiplicative inverse for each number besides 0. And then lastly, we have the distributive property. And what it says, I'm just going to write it down like this. A times B plus C is equal to A times B plus A times C. And that's true for all A, B, and C element of R. I think the book says a little bit more, but that's all I'm going to say. And that's the distributive property. So that's the first fact that we've had for our course in terms of course material. Let me give you a second to write it down. And it's just these facts that we initially can start off with to try to prove things. Just these facts. These assumptions, I should say, or axioms that we're working with for the real numbers. And I think I have time to write down at least the first statement. And maybe it has the first statement that will be approved for the class. At least get it written down. It's got 3 parts. It says, if Z and A are elements of R, that's what it says, with, we're saying this has to happen, Z plus A equals to A, then the conclusion is that Z equals to 0. Part B says, if U and B are elements of R, with B being different from 0, and U times B equals to B, then U had to be 1. And lastly, this is part C of the statement. It says, if A is an element of R, then A times 0 equals to 0. So that's the first statement. I hadn't proven it, but that's the first statement. We can only, we're going to be able to prove this statement, part A of it, only using the 9 properties that we have for the algebraic properties of R. Let me do it real quick, okay? I know it's 150, but let me take 1 minute. So here's part A. Here's proofs. Here's part A. What we're going to do is we're going to let Z and A be element of R with, I can do this directly, with Z plus A equaling A. Okay? We want to show Z equals to 0. Here's what I'm going to do. I'm going to grab Z. Okay? I want to show that Z is equal to 0. So I'm going to start off with Z. So what I know is that Z is the same thing. So I'm going to start. No. Z is the same thing as Z plus 0. That's one of the properties. I can add 0 to anything and I'm still the same thing. Okay? But 0 can be rewritten in terms of A as A plus minus A. So I just replace 0 with A plus minus A. And then reassociating, this says Z plus A plus minus A is the same thing as Z. But by hypothesis, what's Z plus A? We're assuming that Z plus A is equal to something. What is Z plus A equal to? Look up there. A. So that means that this is equal to A plus minus A. But what's A plus minus A? 0. Look at the string. Z equals to all this guy, and at the end we said it's the same thing as, and that's what we're trying to prove. And I'm just using properties, the algebraic properties of R. That's all I did. Okay? To get from one step to the other and do substitution. I'm going to call it quits there. Thank you very much for your time and patience.